Subscribe to the channel so you don't miss out on any of these videos. Imagine a star that seems to age backward, a cosmic cheat code that defies the rules we thought the universe played by. How can an ancient cluster of stars, billions of years old, host some that look suspiciously young, hot, and massive? It's a mystery that leaves scientists scratching their heads, breaking out the calculators, and wondering if the universe has been pulling a fast one all along. These stars are called blue stragglers, and they might just be some of the strangest objects in the cosmos. Before we dive into why these stars are so puzzling, let's talk about how stars usually work. Stars, much like people, go through predictable life stages. They're born, grow, and eventually age, losing their energy and dimming into old age as white dwarfs or exploding in dramatic supernovas. This process is driven by how much mass a star has. Big stars burn bright and fast, living wild but short lives. Smaller stars, like our Sun, take their time, burning steadily for billions of years. It's a system that astronomers understand well, until blue stragglers come along and throw that understanding into chaos. These peculiar stars are found in old star clusters, places that are like retirement homes for stars. Star clusters are dense, gravitationally bound groups of stars that were all born around the same time, from the same massive cloud of gas and dust. Because of this, the stars in a cluster should all be at roughly the same point in their evolutionary journeys. The more massive stars in the cluster should have burned out long ago, leaving behind dim remnants. But blue stragglers don't follow this rule. Instead, they shine brightly and appear much younger than their neighbors. They're hotter, bluer, and more massive than they should be, like finding a teenager in a room full of centenarians. So, how do we explain them? There are a few theories, but none are simple, and all are still being debated. One possibility is that blue stragglers are formed through stellar mergers. In the crowded environment of a star cluster, stars can collide and merge together. When this happens, the resulting star gains mass, becoming hotter and brighter. This new star can look young, even though it's made of material that's billions of years old. Essentially, it's like taking two old, tired stars and combining them to make one that looks fresh and energetic. Another explanation involves mass transfer in binary star systems. Binary stars are pairs of stars that orbit each other, bound together by gravity. If one star in the pair expands, say, during its red giant phase, it can transfer some of its material to its companion. The receiving star bulks up, gaining enough mass to heat up and shine like a younger star. This process doesn't create a new star, but it does rejuvenate an existing one, giving it a second lease on life. But even these explanations raise more questions than they answer. For one, if collisions are responsible for blue stragglers, how often do these collisions happen, and why do we see them in some clusters but not others? Star clusters are dense, but the distances between stars are still vast. Collisions should be rare. And if mass transfer in binaries is the culprit, how does this process work so efficiently? And why doesn't it happen in every binary system? Observations of blue stragglers also reveal another layer of complexity. These stars aren't evenly distributed throughout their clusters. Instead, they tend to be found closer to the cluster's core. This makes sense if interactions like collisions or binary mass transfer are responsible, since the core is the most crowded part of a cluster, where stars are packed tightly together. But this raises yet another question. Why don't we see blue stragglers in every dense cluster? The puzzle of blue stragglers isn't just an academic curiosity. It has implications for our understanding of stellar evolution, the dynamics of star clusters, and even the life cycles of galaxies. For example, studying blue stragglers helps astronomers refine their models of how stars interact in crowded environments. It also provides clues about how star clusters evolve over time, including how they lose mass and eventually dissolve. The phenomenon of blue stragglers also challenges one of the most fundamental assumptions in astronomy, that stars in a cluster can be used as a kind of clock to date the cluster itself. If blue stragglers are present, they can skew the results, making the cluster appear younger than it really is. This has led scientists to develop new techniques for identifying and accounting for these rogue stars when estimating the ages of star clusters. And then there's the question of how blue stragglers affect their surroundings. When a star gains mass, it also gains gravity, which can influence the orbits of nearby stars. In some cases, a blue straggler might even eject other stars from the cluster, altering its overall structure. These subtle effects can add up over millions or billions of years, changing the way clusters evolve and interact with their host galaxies. Despite decades of research, blue stragglers remain an enigma. Advances in technology, like high-resolution telescopes and computer simulations, are helping scientists probe deeper into this mystery. For example, data from space-based observatories like Hubble have provided detailed images of star clusters, allowing astronomers to identify and study blue stragglers in greater detail. Simulations of stellar collisions and binary interactions are also shedding light on the physical processes that might create these stars. But for every answer, new questions arise. Are there different types of blue stragglers, created through different mechanisms? Could there be factors we haven't even considered yet, like the influence of dark matter or magnetic fields? And what do blue stragglers tell us about the broader universe, about the hidden complexities lurking in systems we thought we understood? Blue stragglers remind us that the universe is full of surprises. Just when we think we have it all figured out, a star comes along and says, "Not so fast." These cosmic rebels challenge our assumptions and push the boundaries of what we know, sparking curiosity and inspiring the next generation of discovery. The deeper we delve into the phenomenon of blue stragglers, the more we realize that their existence reshapes our understanding of cosmic evolution. While the leading theories of stellar mergers and mass transfer in binary systems explain much, they also leave behind a trail of unresolved mysteries. To truly grasp the significance of these stars, we need to dig into the finer details of their behavior, origins, and the ripple effects they have on their environments. Take, for instance, the concept of stellar mergers. At first glance, the idea of two stars colliding sounds dramatic and rare, but in the dense cores of star clusters, the chances increase significantly. These regions are packed with stars moving at high velocities, and their close proximity creates opportunities for gravitational interactions. However, even with these conditions, direct collisions are not as straightforward as they seem. Stars are not solid objects. They are massive spheres of gas and plasma. When two stars approach each other, their outer layers can interact long before their cores collide. This interaction can lead to the stripping of outer layers or the gradual merging of material, forming a single, rejuvenated star. The challenge for scientists is to model these interactions accurately. Simulations suggest that the likelihood of mergers depends on the density of the cluster, the relative velocities of the stars, and the presence of external forces like tidal interactions from a nearby galaxy. But even with sophisticated models, predicting the exact conditions that lead to blue stragglers remains a daunting task. This uncertainty is part of what makes blue stragglers so fascinating. They are a cosmic wildcard, an outcome of chaotic processes that defy easy explanation. Now let's examine the alternative theory, mass transfer in binary systems. Binary stars are incredibly common in the universe, with many stars existing in pairs or even larger systems. In these partnerships, the two stars influence each other's evolution. When one star expands into a red giant, its outer layers can spill over onto its companion. This transfer of mass alters the fate of both stars. The donor star loses mass and may end its life as a lightweight white dwarf, while the recipient star gains mass, reigniting fusion reactions in its core and shining brightly as a blue straggler. One of the intriguing aspects of this process is the precision required for it to occur. If the stars are too far apart, mass transfer won't happen. If they are too close, the interaction can lead to a more violent outcome, like a nova or a complete merger. The balance must be just right for the transfer to produce a stable, rejuvenated star. Observing such systems in action is rare, but astronomers have identified a few binary systems that seem to fit the profile, providing valuable clues about how blue stragglers form. Beyond their origins, blue stragglers raise important questions about the long-term evolution of star clusters. These stars don't just sit quietly in their clusters. They interact with their surroundings in complex ways. For example, their increased mass gives them stronger gravitational pull, which can disrupt the orbits of nearby stars. Over time, this gravitational influence can alter the structure of the cluster, concentrating stars in the core or ejecting them into interstellar space. There's also the matter of chemical composition. Studies of blue stragglers reveal that they often have unusual elemental abundances compared to their neighbors. This is particularly evident in cases of mass transfer, where the recipient star may be enriched with helium and other elements from its companion. These chemical signatures provide important evidence for unraveling the history of these stars, acting as a kind of cosmic fingerprint that points to their origins. But even with all this data, some blue stragglers remain stubbornly enigmatic. In certain clusters, these stars appear without any obvious signs of mergers or mass transfer. This has led scientists to propose additional mechanisms, such as the influence of unseen companions like black holes or neutron stars. These compact objects could interact with ordinary stars in ways that mimic the effects of mergers or mass transfer, creating blue stragglers through entirely different processes. Another intriguing question is why blue stragglers are found primarily in certain types of star clusters. Globular clusters, which are among the oldest structures in the universe, are particularly rich in these stars. Open clusters, by contrast, have far fewer blue stragglers. This difference may be related to the density and age of the clusters. Globular clusters are densely packed and have had billions of years for interactions to occur, creating the perfect conditions for blue stragglers to form. Open clusters, being younger and less dense, may not experience the same level of stellar interactions. The distribution of blue stragglers within clusters also offers valuable insights. As mentioned earlier, these stars tend to be concentrated in the cores of their clusters. This is consistent with the idea that their formation is linked to interactions in dense environments. However, in some clusters, blue stragglers are also found in the outskirts, raising questions about how they got there. One possibility is that these stars were ejected from the core through gravitational interactions, a process known as dynamical friction. This would explain their presence in less crowded regions, but it also suggests that the story of blue stragglers is far more dynamic than we might have imagined. Astronomers have also used blue stragglers as tools for studying the history of their clusters. By analyzing the properties of these stars, scientists can infer details about the cluster's past, such as its initial mass, density, and rate of stellar interactions. In this way, blue stragglers act as cosmic archaeologists, preserving a record of the conditions that shaped their formation. Despite all the progress that has been made, the mystery of blue stragglers is far from solved. Each new discovery seems to raise as many questions as it answers, keeping this field of research vibrant and exciting. As we continue to explore the universe with ever more powerful telescopes and sophisticated simulations, the secrets of these enigmatic stars may finally come to light. But until then, they remain one of the universe's most tantalizing puzzles. A reminder that even in a cosmos as vast and ancient as ours, there are still surprises waiting to be uncovered. As we continue exploring the mystery of blue stragglers, it's important to consider how technological advancements are reshaping our ability to study these enigmatic stars. The past few decades have seen incredible leaps in telescope technology, computational modeling, and observational techniques, all of which have provided us with new tools to peel back the layers of this cosmic puzzle. One of the most significant breakthroughs has come from space-based telescopes like the Hubble Space Telescope. Hubble's ability to capture high-resolution images of dense star clusters has been instrumental in identifying blue stragglers and distinguishing them from other types of stars. By observing clusters like 47 Tucani or Messier 3, astronomers have catalogued hundreds of blue stragglers, studying their positions, brightness, and spectra in unprecedented detail. These observations have confirmed many theoretical predictions while also revealing anomalies that challenge our understanding. For instance, spectroscopic studies using Hubble and ground-based telescopes have allowed scientists to analyze the light emitted by blue stragglers, providing clues about their chemical compositions. In some cases, astronomers have detected unusual levels of helium or heavy elements like carbon and nitrogen, which are inconsistent with standard stellar evolution models. These anomalies often point to mass transfer or mergers as their origin, but there are still cases where no clear explanation emerges. Meanwhile, computational simulations have become a cornerstone of blue straggler research. Using supercomputers, astrophysicists can model the complex gravitational interactions that occur in dense star clusters, simulating millions of years of evolution in a matter of days. These simulations allow scientists to test different formation scenarios, such as collisions, mergers, and mass transfer, under a variety of conditions. By comparing the results to real observations, researchers can refine their theories and identify the most likely pathways for blue straggler formation. One intriguing result from these simulations is the discovery that blue stragglers can form in multiple waves over the lifetime of a cluster. Early in a cluster's history, when it is still compact and densely packed, direct collisions between stars may dominate. Later, as the cluster expands and interactions become less frequent, mass transfer in binary systems may take over as the primary mechanism. This evolutionary progression helps explain why blue stragglers are found in clusters of all ages, though their numbers and properties can vary significantly. Beyond individual clusters, astronomers are also beginning to investigate whether blue stragglers exist in other environments, such as the field populations of galaxies. While the majority of known blue stragglers reside in star clusters, there is growing evidence that similar stars can be found scattered throughout the Milky Way. These field blue stragglers likely formed through binary interactions rather than collisions, as the density of stars in galactic fields is far too low for frequent mergers. Studying these stars could provide additional insights into the processes that create blue stragglers and their relationship to stellar evolution on a broader scale. One particularly fascinating development in this field is the use of astroseismology to study blue stragglers. This technique involves analyzing the oscillations or starquakes that occur within a star, which can reveal details about its internal structure and composition. By applying this method to blue stragglers, astronomers can probe their cores directly, testing predictions about how they form and evolve. Preliminary results from astroseismic studies suggest that some blue stragglers have unusual core structures, consistent with a history of mergers or mass accretion. The role of blue stragglers in the broader context of galaxy evolution is another area of active research. These stars are not just isolated anomalies. They have implications for the dynamics and longevity of the clusters they inhabit. For example, the presence of massive blue stragglers can influence the gravitational potential of a cluster, affecting the orbits of nearby stars and even altering the cluster's overall shape. Over time, these interactions can lead to the evaporation of stars from the cluster or the formation of a denser core, processes that play a key role in the life cycle of star clusters. Furthermore, blue stragglers may provide clues about the history of binary star systems and their role in the universe. Binary systems are thought to be the birthplace of many exotic phenomena, including supernovae, black holes, and gravitational wave events. By studying blue stragglers, we can gain a better understanding of how binaries interact and evolve, shedding light on these more extreme cosmic events. Despite these advancements, many questions about blue stragglers remain unanswered. For example, why do some clusters have significantly more blue stragglers than others, even when their overall properties are similar? Are there yet undiscovered processes that contribute to their formation? And what can blue stragglers tell us about the environments in which they form? These questions continue to drive research, ensuring that blue stragglers remain a topic of fascination for years to come. Looking ahead, the next generation of telescopes promises to revolutionize our understanding of these stars. Projects like the James Webb Space Telescope, the Vera Rubin Observatory, and the European Extremely Large Telescope will provide unprecedented views of star clusters, allowing astronomers to study blue stragglers in greater detail than ever before. These instruments will be able to detect fainter stars, observe in different wavelengths of light, and capture the subtle motions of stars over time, all of which are crucial for unraveling the mysteries of blue stragglers. In addition to telescopes, new missions like Gaia are providing a wealth of data on the positions, motions, and properties of stars across the Milky Way. By combining Gaia's data with observations from other telescopes, astronomers can map the distribution of blue stragglers throughout the galaxy, identifying patterns that might reveal new clues about their origins. At the same time, Advances in computational power and machine learning are enabling scientists to analyze vast datasets more efficiently. These tools can identify subtle trends and correlations that might be missed by traditional methods, offering new perspectives on the nature of blue stragglers and their role in the universe. Ultimately, the mystery of blue stragglers is a testament to the complexity and beauty of the cosmos. These stars challenge our assumptions, forcing us to rethink our models and question our understanding of how the universe works. They remind us that even in a field as well studied as stellar astronomy, there is always more to learn, always another mystery waiting to be solved. The quest to understand blue stragglers is far from over. With each new discovery, we inch closer to the truth, uncovering not only the secrets of these stars but also the deeper workings of the universe itself. And in that journey, blue stragglers remain a shining beacon, a reminder of the endless possibilities that lie beyond our reach, waiting to be explored. The search for answers about blue stragglers is a scientific journey that continues to evolve, guided by an ever-growing arsenal of technology and insights. As researchers delve deeper, the implications of these enigmatic stars stretch far beyond their immediate characteristics, offering profound insights into the interconnected processes of stellar evolution, cluster dynamics, and the larger fabric of the universe. One emerging avenue of exploration lies in the study of metallicity. In astrophysics, metallicity refers to the abundance of elements heavier than hydrogen and helium in a star. Blue stragglers, like other stars, exhibit unique metallicity profiles that can provide valuable information about their formation and evolutionary history. For example, stars formed through mass transfer may show enhanced levels of elements like helium and carbon due to material stripped from a donor star's outer layers. By carefully analyzing the metallicity of blue stragglers across various clusters, scientists can better understand the chemical fingerprints of different formation mechanisms. Interestingly, studies have revealed that clusters with higher metallicity tend to host fewer blue stragglers. This counterintuitive trend has sparked debates in the scientific community, as it suggests that the metallicity of a cluster's stars might influence the efficiency of the processes that create blue stragglers. Could metallicity affect the likelihood of binary systems evolving into mass transfer pairs? Or perhaps it alters the dynamics of stellar collisions? These are the kinds of questions driving ongoing investigations. The role of environment in shaping blue straggler populations is another intriguing puzzle. Star clusters are diverse ecosystems, ranging from sparse open clusters with loosely bound stars to dense globular clusters packed with millions of stars in close proximity. The physical conditions within these clusters, such as density, temperature, and gravitational interactions, create vastly different environments that can influence the formation and survival of blue stragglers. In dense clusters, where collisions are more common, blue stragglers formed through mergers might dominate. Conversely, in more diffuse environments, mass transfer between binary stars could become the primary mechanism. This environmental dependency offers a fascinating opportunity to use blue stragglers as cosmic laboratories, helping us understand how stars behave under different conditions. For instance, the core of a globular cluster is often teeming with stars packed so tightly that gravitational interactions become inevitable. These interactions can lead to the ejection of stars, the disruption of binary systems, or even the formation of exotic objects like intermediate mass black holes. Blue stragglers, as products of such dynamic environments, serve as a visible reminder of the chaotic processes at play in these stellar nurseries. Moreover, blue stragglers provide critical clues about the age of star clusters. Typically, astronomers determine the age of a cluster by examining its Hertzsprung-Russell diagram, which plots the brightness and temperature of stars. The point where stars begin to leave the main sequence, the so-called turn-off point, indicates the cluster's age. However, the presence of blue stragglers complicates this method, as their seemingly youthful characteristics can skew the interpretation of the turn-off point. By accounting for blue stragglers and their formation pathways, astronomers can refine age estimates, leading to more accurate models of cluster evolution. The importance of blue stragglers extends beyond the confines of individual star clusters. They may also hold the key to understanding broader galactic processes. For example, the study of blue stragglers in the Milky Way's halo, an ancient, sparsely populated region surrounding the galaxy, offers insights into the galaxy's early history. These halo blue stragglers are thought to have originated in globular clusters that were later disrupted, scattering their stars across the galaxy. By tracing the origins of these stars, researchers can reconstruct the formation and assembly history of the Milky Way itself. At the same time, blue stragglers challenge our understanding of stellar lifespans. In a universe governed by entropy, where everything ages and decays, these stars seem to defy the natural order. Their prolonged main sequence lives raise questions about the universality of stellar evolution models. If exceptions like blue stragglers exist, might there be other, yet undiscovered processes that allow stars to cheat death in different ways? This prospect keeps scientists on their toes, constantly reevaluating the assumptions underlying their theories. Another intriguing aspect of blue stragglers is their potential role in the formation of exotic objects, such as millisecond pulsars and neutron stars. In binary systems where one star evolves into a compact object, the accretion of material from a companion can spin up the compact object to incredibly high rotation speeds, creating a millisecond pulsar. If the companion is a blue straggler, its prolonged lifespan could sustain this process over longer timescales, influencing the population and characteristics of these exotic remnants. The influence of blue stragglers even extends into the realm of gravitational wave astronomy. Collisions and mergers in dense star clusters, which are known to produce blue stragglers, may also create tight binary systems of compact objects like black holes or neutron stars. These binaries are prime sources of gravitational waves, ripples in spacetime detected by observatories like LIGO and Virgo. By studying the environments that give rise to blue stragglers, we gain indirect insights into the processes that produce these gravitational wave events. While we've made significant strides in understanding blue stragglers, many mysteries remain unsolved. For example, why do some clusters appear to lack blue stragglers altogether? Are there certain conditions that entirely suppress their formation? And could there be undiscovered types of blue stragglers that defy even our most flexible models? These questions highlight the dynamic and ever-evolving nature of astrophysical research. As we peer further into the cosmos, new discoveries about blue stragglers are sure to emerge, driven by next-generation observatories and innovative approaches to data analysis. These stars, though small in number compared to the vast populations of ordinary stars, punch well above their weight in terms of the insights they offer. They remind us that the universe is not a static place, but a dynamic and ever-changing tapestry where the unexpected is not just possible, but inevitable. The enigma of blue stragglers serves as a poignant reminder of how much we still don't know about the universe. These stars, which seem to defy the natural order, challenge us to think beyond the obvious and embrace the complexities of nature. In doing so, they inspire a sense of wonder and curiosity that fuels the very essence of scientific exploration. Whether through collisions, mergers, or some other as yet undiscovered mechanism, blue stragglers stand as a testament to the universe's capacity for surprise, reminding us that the cosmos always has more to teach. The mystery of blue stragglers continues to inspire some of the most fascinating questions in astrophysics, not just because of what they reveal about stars but also because of what they imply about the broader cosmic environment. These enigmatic objects remind us that the universe often operates in ways we do not yet fully understand. Every new discovery about them deepens our comprehension of stellar evolution, while simultaneously posing new challenges to existing theories. One particularly compelling aspect of blue stragglers is their relationship with dark matter, the elusive substance that makes up most of the universe's mass. While not directly tied to the phenomenon of blue stragglers, dark matter plays a significant role in shaping the environments where these stars are found, particularly in the dense cores of globular clusters. Could the gravitational influence of dark matter indirectly affect the dynamics of star collisions and mergers? This speculative but intriguing idea underscores how interconnected different areas of astrophysics can be. Even phenomena that seem unrelated at first glance may turn out to be crucial pieces of a larger cosmic puzzle. In the search for answers, astronomers have also turned to computer simulations, which allow them to model the complex interactions that lead to blue straggler formation. By simulating millions of years of cluster dynamics in a virtual environment, researchers can test various scenarios, such as binary mass transfer, stellar mergers, and gravitational interactions. These simulations have provided crucial insights, such as predicting the rates at which blue stragglers form and their expected lifetimes. However, even the most advanced simulations face limitations, as they depend on the accuracy of the input data and assumptions. For instance, small variations in initial conditions, like the mass distribution of stars or the density of a cluster, can lead to drastically different outcomes, highlighting the need for continual refinement of these models. One of the most fascinating implications of blue stragglers is their potential role as markers of time. Traditional methods of dating star clusters rely on observing the main sequence turn-off point, where stars begin transitioning into later stages of their lives. However, the presence of blue stragglers complicates this method, as their youthful appearance can skew the turn-off point. By understanding how and why blue stragglers form, astronomers can develop more accurate models for interpreting cluster ages. This has far-reaching implications, not just for studying individual clusters but also for piecing together the broader timeline of galactic evolution. Furthermore, blue stragglers might hold clues to the ultimate fates of star clusters. Over billions of years, clusters lose stars through processes like tidal stripping, where gravitational interactions with the galaxy pull stars away. Blue stragglers, often found in the dense cores of clusters, could serve as indicators of the dynamical processes at work in these environments. By studying the distribution and behavior of blue stragglers, researchers can gain insights into how clusters evolve, dissolve, or merge over time. The study of blue stragglers also has practical applications for future space exploration. Understanding how stars interact in dense environments can inform the planning of missions to regions with high stellar densities, such as the centers of globular clusters. For example, if we ever send spacecraft to explore these regions, knowing the likelihood of stellar collisions and the presence of unusual stars like blue stragglers will be crucial for navigation and mission safety. These considerations demonstrate how theoretical astrophysics can have real-world implications, even in the context of humanity's long-term aspirations to explore the stars. Interestingly, blue stragglers also serve as a reminder of the interconnectedness of life and the cosmos. Stars are the factories of the universe, producing the heavy elements necessary for planets and ultimately for life itself. By understanding the processes that allow certain stars to cheat aging, we gain deeper insights into the life cycle of stars and their contributions to the cosmic ecosystem. Blue stragglers may be anomalies, but they are also a testament to the diversity and complexity of the universe, where even the outliers play a crucial role in the grand narrative of existence. As our technological capabilities continue to grow, so too does our ability to study blue stragglers in greater detail. Next-generation telescopes, like the James Webb Space Telescope and the upcoming Extremely Large Telescope, will allow astronomers to observe these stars with unprecedented precision. These instruments will enable detailed spectroscopic analyses, revealing the chemical compositions, temperatures, and rotational velocities of blue stragglers. Such data will be invaluable for testing existing theories and potentially uncovering new mechanisms behind their formation. The role of citizen science in advancing our understanding of blue stragglers is also worth noting. Projects like Galaxies Zoo and other crowdsourced initiatives have demonstrated the power of engaging the public in scientific discovery. By analyzing data from telescopes and simulations, amateur astronomers and enthusiasts can contribute to identifying and cataloging blue stragglers and star clusters across the galaxy. This collaborative approach not only accelerates the pace of discovery, but also fosters a deeper appreciation for the wonders of the universe among people from all walks of life. The study of blue stragglers is as much about asking questions as it is about finding answers. Why do some clusters have more blue stragglers than others? What role do these stars play in the larger context of cluster dynamics and galactic evolution? Are there other, yet undiscovered processes that allow stars to defy aging in even more unexpected ways? Each of these questions represents a frontier of exploration, pushing the boundaries of what we know and challenging us to think creatively about the universe. The mystery of blue stragglers exemplifies the beauty of science, the idea that every answer leads to new questions, and that the pursuit of knowledge is an endless journey. As we continue to explore the cosmos, these enigmatic stars will remain a symbol of the universe's capacity for surprise and a testament to humanity's unyielding curiosity. The story of blue stragglers is far from over, and as new discoveries emerge, they will undoubtedly reshape our understanding of the cosmos in ways we cannot yet imagine. The pursuit of understanding blue stragglers doesn't just reside within the boundaries of theoretical astrophysics. It bridges multiple scientific disciplines and unveils deeper truths about the cosmos. Each discovery about these anomalous stars peels back another layer of the universe's enigmatic behavior. As astronomers study them further, one theme persists: the rules of physics and stellar evolution are guidelines, not absolutes. Nature, in its creativity, seems to find loopholes. Consider for a moment the sheer improbability of blue stragglers existing. A typical star cluster forms together from the same molecular cloud, giving all its stars roughly the same age and composition. Over time, these stars follow predictable evolutionary paths determined by their initial mass and size. Massive stars burn brightly and die young, while smaller stars live longer, fainter lives. Yet, in some clusters, blue stragglers appear, stars seemingly too massive and youthful to belong to their ancient surroundings. This mystery flies in the face of these fundamental principles, like discovering an athlete running their fastest marathon long after retirement age. One critical question is whether blue stragglers are rare anomalies or a natural consequence of stellar evolution in dense environments. Studies of globular clusters suggest they may be relatively common under certain conditions. Observations reveal that the frequency of blue stragglers correlates with the density of a cluster's core. Denser cores provide more opportunities for close encounters, binary interactions, and even direct collisions, all of which can lead to the rejuvenation process that gives rise to these stars. In sparser regions, such interactions are far less likely, which explains why blue stragglers are less prevalent there. However, even in dense environments, the exact mechanisms remain elusive. Binary star systems offer one plausible explanation. In these systems, one star can transfer its mass to its companion, effectively revitalizing it. This mass transfer causes the companion to shine more brightly and appear younger, even though it retains the age of the cluster. The donor star, having given up much of its material, evolves more quickly into a compact remnant, such as a white dwarf. This scenario is supported by the fact that many blue stragglers are found in binary systems, and their companions are often remnants of once larger stars. Another intriguing mechanism involves stellar mergers. In clusters with high stellar densities, stars can come into close proximity, occasionally colliding and merging. When two stars merge, they combine their masses into a single, more massive entity. This new star, though technically as old as the original stars, appears youthful because of its increased mass and energy output. Stellar mergers are dramatic events, involving intense gravitational interactions and the release of enormous amounts of energy. They are also rare, making them difficult to observe directly, but their fingerprints are seen in the characteristics of blue stragglers. The dynamical processes behind blue stragglers provide unique insights into the life cycles of star clusters. Over time, gravitational interactions within a cluster cause it to undergo core collapse, where the center becomes increasingly dense. This collapse brings stars closer together, increasing the likelihood of the interactions that form blue stragglers. Thus, the presence of these stars serves as a marker of a cluster's evolutionary stage. In some cases, the number of blue stragglers might even help astronomers estimate how long a cluster has been undergoing core collapse. What's fascinating is how blue stragglers blur the lines between stellar aging and rejuvenation. While traditional models treat stars as isolated objects evolving independently, the study of blue stragglers highlights the importance of external influences. These stars do not age in isolation. Their evolution is shaped by their interactions with other stars and their environment. This interconnectedness challenges the notion of stars as solitary entities, suggesting instead that their fates are intertwined. In recent years, new technologies have revolutionized the study of blue stragglers. Instruments like the Hubble Space Telescope have provided unprecedented views of star clusters, allowing astronomers to identify and analyze these peculiar stars in detail. High-resolution imaging and spectroscopy have revealed the chemical compositions, surface temperatures, and rotational velocities of blue stragglers, providing crucial data for testing theoretical models. Moreover, advanced simulations have enabled researchers to recreate the conditions in star clusters, offering insights into how blue stragglers might form and evolve over time. One emerging area of research involves the role of magnetic fields. Magnetic fields can influence the behavior of stars, affecting their rotation rates, mass loss, and energy output. Some astronomers speculate that magnetic interactions within binary systems or during stellar mergers might play a role in the formation of blue stragglers. If true, this would add another layer of complexity to the already intricate processes involved. Another fascinating aspect of blue stragglers is their potential connection to exotic objects like neutron stars and black holes. In dense clusters, interactions with these compact remnants could influence the formation of blue stragglers. For example, a binary system containing a neutron star might undergo complex gravitational interactions, leading to mass transfer or the ejection of one star, leaving behind a blue straggler. These scenarios are still speculative but represent an exciting frontier in astrophysics. As scientists probe deeper into the nature of blue stragglers, they are uncovering not just answers but also new questions. For instance, why do some clusters have disproportionately large numbers of blue stragglers? Is there a connection between the chemical composition of a cluster and the prevalence of these stars? Are there unknown processes at work that have yet to be discovered? Each of these questions drives further research, pushing the boundaries of our understanding. What makes blue stragglers so captivating is their defiance of expectations. They are reminders that the universe is not a static place governed by rigid rules but a dynamic, evolving system full of surprises. For astronomers, these stars represent an opportunity to challenge existing theories and develop new ones. For the rest of us, they are a testament to the beauty and complexity of the cosmos, a reminder that even in a universe as vast as ours, there are still mysteries waiting to be unraveled. The story of blue stragglers is far from complete. With every new observation, every new theory, and every new discovery, we come closer to understanding these enigmatic stars. But as with all great mysteries, the journey is just as important as the destination. Blue stragglers remind us to keep asking questions, to keep exploring, and to never stop marveling at the universe's capacity to surprise us. The mystery of blue stragglers also connects to a broader philosophical and scientific principle. The cosmos doesn't conform neatly to human expectations. Our understanding of stellar evolution, for instance, is based on models and theories that aim to simplify an incredibly complex system. When phenomena like blue stragglers defy these models, they force us to rethink and refine our understanding, making science not just a collection of facts but a living, evolving process. The peculiar characteristics of blue stragglers also challenge long-standing assumptions about how isolated and predictable stellar evolution can be. Instead of evolving according to their initial mass and age, these stars have their lifespans rewritten through environmental interactions. This blurs the boundary between the intrinsic nature of a star and the extrinsic influences that alter its fate. It suggests that, much like the complex dynamics of ecosystems on Earth, star clusters are interactive environments where individual components influence one another profoundly. One of the most exciting questions concerns whether blue stragglers can exist in isolation, outside dense star clusters. Could these rejuvenated stars form in more typical galactic environments, such as our solar neighborhood? Observations of nearby stars have identified candidates that share similar characteristics with blue stragglers, prompting debates about whether they might have experienced unique histories involving binary systems or even past collisions. These isolated blue straggler analogs could help scientists unravel whether their formation requires the specific gravitational dynamics of dense clusters or if other processes are at play. Another angle to the blue straggler enigma is their surprising longevity. These stars, after gaining additional mass, not only appear younger but also extend their lifetimes beyond what their original mass would have allowed. The infusion of fresh hydrogen into their cores, whether through mass transfer or merger, acts as a kind of cosmic reset button. This delay in their aging process grants astronomers a unique opportunity to study stars that otherwise would have long since faded into stellar remnants. Blue stragglers also hold tantalizing clues about the ultimate fate of star clusters themselves. Globular clusters, home to many blue stragglers, are some of the oldest structures in the universe, dating back billions of years. Yet, these clusters are not static. Over time, gravitational interactions cause stars to migrate, collide, and even be ejected entirely. Blue stragglers act as tracers of these processes. By studying their distribution and frequency, astronomers can piece together a timeline of a cluster's history and predict its eventual dissolution. Interestingly, the role of blue stragglers extends beyond the confines of their clusters. Their unusual brightness and extended lifetimes make them valuable for calibrating astronomical tools and measurements. For example, their distinct properties help refine models of stellar populations, which are crucial for understanding distant galaxies. In a way, blue stragglers serve as cosmic benchmarks, helping scientists decode the light from galaxies billions of light-years away. One of the most puzzling aspects of blue stragglers is their rotational speeds. Observations reveal that many of these stars spin significantly faster than other stars of similar mass and age. This rapid rotation is thought to result from the processes that create them, whether it's the angular momentum transfer during a merger or the accretion of material in a binary system. Rapid rotation has profound effects on a star's structure and evolution, influencing everything from its shape to its magnetic fields. Understanding how blue stragglers manage this excess angular momentum could shed light on the physics of stellar interiors. As technology advances, so does our ability to study blue stragglers in unprecedented detail. Future missions, such as the James Webb Space Telescope, promise to revolutionize our understanding of these stars. With its powerful infrared capabilities, the telescope can peer deeper into star clusters, analyzing the faint companions or remnants that might hold clues to the origins of blue stragglers. Additionally, ground-based observatories equipped with adaptive optics can provide sharper images of crowded cluster cores, where these stars are often found. Blue stragglers are also a reminder of the importance of collaboration in science. Solving the mystery of their existence requires input from multiple disciplines, including astrophysics, computational modeling, and even nuclear physics. Each piece of the puzzle, whether it's the dynamics of binary systems, the outcomes of stellar collisions, or the chemical fingerprints left by mass transfer, requires expertise from different fields. This interdisciplinary approach highlights the interconnected nature of scientific discovery, where progress in one area often leads to breakthroughs in another. Another intriguing possibility is that blue stragglers could serve as windows into the early universe. Globular clusters, where many blue stragglers are found, are ancient structures that formed during the galaxy's infancy. By studying these clusters and their enigmatic stars, astronomers can gain insights into the conditions that prevailed during the early stages of galaxy formation. This adds a cosmological dimension to the blue straggler puzzle, linking their study to some of the most profound questions about the origins of the universe itself. But perhaps the most captivating aspect of blue stragglers is their story, one of defiance, resilience, and cosmic transformation. These stars remind us that the universe is full of surprises, constantly challenging our assumptions and expanding our horizons. They are a testament to the power of curiosity, showing that even the smallest anomalies can lead to profound insights about the nature of reality. As researchers continue to probe the secrets of blue stragglers, they are not just unraveling a single mystery but opening the door to new realms of understanding. Each observation, each theory, each discovery adds to a growing tapestry of knowledge, illuminating the complex and beautiful workings of the cosmos. And while the ultimate answers may still elude us, the journey itself is a testament to humanity's enduring quest for knowledge, a quest driven by the simple yet profound desire to know more. Blue stragglers highlight a fundamental truth about the cosmos. It is a dynamic, ever-changing environment where phenomena evolve and interact in ways that defy simplistic categorization. These stars, which appear as youthful anomalies in an otherwise aged stellar population, emphasize the complexity of star cluster ecosystems and the intricate ballet of gravitational forces, collisions, and interactions that shape their evolution. The more astronomers uncover about blue stragglers, the clearer it becomes that these stars are not mere oddities. Instead, they represent a critical chapter in the story of stellar evolution, demonstrating the extraordinary influence of interactions between stars. In tightly packed regions like globular clusters, the probability of close encounters or binary system interactions increases dramatically, providing the perfect laboratory to observe processes that might be rare or difficult to detect in more isolated environments. One of the fascinating implications of studying blue stragglers is their potential to reveal hidden populations of binary systems and star clusters. Binary systems are pairs of stars gravitationally bound to each other, and they play an outsized role in the life cycles of star clusters. When one star in a binary system begins transferring mass to its companion, or when the two stars merge, it fundamentally alters their evolutionary paths, often giving rise to a blue straggler. By identifying and studying these stars, scientists can infer the frequency and properties of binary systems and clusters, providing insight into the complex web of relationships that shape these ancient stellar communities. The presence of blue stragglers also raises intriguing questions about the ultimate fate of globular clusters themselves. These ancient structures are home to some of the universe's oldest stars, but they are not eternal. Over billions of years, gravitational interactions between stars gradually erode the cluster's mass, causing stars to drift away into interstellar space. Blue stragglers, as products of mass transfer or mergers, could offer clues about how these processes unfold. For example, their distribution within a cluster can reveal information about the cluster's internal dynamics and gravitational history, helping scientists piece together its past and predict its eventual disintegration. Interestingly, blue stragglers might also influence the chemical evolution of their host clusters. When a star gains mass through accretion or merger, its internal structure is altered, potentially affecting the way it synthesizes and releases elements. Over time, these stars could contribute unique chemical signatures to the cluster, providing a record of the dynamic processes that shaped its evolution. By studying these signatures, astronomers can gain deeper insights into the life cycle of stars and the chemical enrichment of the universe. Another layer of mystery involves the potential role of blue stragglers in starburst events, periods of intense star formation that can reshape a galaxy or cluster. While blue stragglers themselves are not newborn stars, their formation mechanisms suggest that they could act as catalysts for energetic phenomena within dense stellar environments. For example, the gravitational interactions that lead to blue straggler formation could also trigger the collapse of nearby gas clouds, igniting new waves of star formation. This connection between stellar dynamics and broader galactic processes underscores the interconnectedness of cosmic events. Blue stragglers also challenge our understanding of stellar populations in a broader context. Traditionally, astronomers have used the color magnitude diagram, a plot of stars' brightness versus their color, or temperature, to study stellar evolution. In this framework, stars follow well-defined paths based on their initial mass and composition. However, blue stragglers deviate from these paths, occupying regions of the diagram that seem inconsistent with their presumed age. This deviation forces scientists to reconsider how such diagrams should be interpreted, particularly in environments where interactions between stars are common. The rotational properties of blue stragglers add yet another layer of complexity. Rapid rotation can influence a star's shape, causing it to bulge at the equator and flatten at the poles. This, in turn, affects the star's luminosity and temperature, creating subtle but measurable differences in its observed characteristics. Understanding these effects is crucial for accurately interpreting the data collected by telescopes, especially when studying distant star clusters or galaxies. It also raises the question of whether blue stragglers might serve as proxies for studying rotational dynamics in other types of stars. One of the most exciting frontiers in blue straggler research is the application of advanced computational models. Simulating the complex interactions that lead to blue straggler formation requires significant computational power and sophisticated algorithms. By running simulations of binary systems, stellar collisions, and cluster dynamics, scientists can test different hypotheses and compare the results with observational data. These models not only help unravel the mystery of blue stragglers but also provide valuable tools for studying other astrophysical phenomena, from black hole formation to the behavior of exoplanetary systems. The search for blue stragglers outside of globular clusters is also gaining momentum. While most known examples are found in these dense environments, similar stars have been identified in open clusters and even in the field, regions of space outside any cluster. These discoveries suggest that the processes leading to blue straggler formation might be more widespread than previously thought. They also open the door to studying these stars in a variety of contexts, potentially uncovering new mechanisms for their creation. As technology continues to advance, so does our ability to study blue stragglers in greater detail. High-resolution spectroscopy, for instance, allows astronomers to analyze the chemical composition of these stars, revealing clues about their history and formation. Similarly, long-term monitoring of star clusters can track the evolution of blue stragglers over time, providing a dynamic view of their life cycles. With each new observation, the story of these enigmatic stars becomes richer and more complex, offering fresh opportunities for discovery. Ultimately, blue stragglers are more than just a puzzle to be solved. They are a reminder of the boundless curiosity that drives science, the endless questions that arise as we explore the universe, and the profound sense of wonder that comes from uncovering its secrets. These stars, which defy expectations and challenge established theories, embody the spirit of discovery, inspiring us to look deeper, think harder, and never stop asking questions. As researchers continue their quest to understand blue stragglers, they are not just uncovering the mysteries of these stars, they are also pushing the boundaries of human knowledge, venturing into the unknown, and redefining what we know about the cosmos. And in doing so, they remind us that the universe is a place of infinite possibilities, filled with wonders that await discovery. The journey into understanding blue stragglers extends far beyond the stars themselves. These stellar anomalies force us to confront profound questions about the nature of the universe, the limits of human understanding, and the processes that govern cosmic evolution. They serve as a bridge between the known and the unknown, challenging astronomers to refine their models and assumptions while embracing the mysteries that persist. One of the most compelling aspects of blue stragglers is their potential to redefine our understanding of stellar longevity. By appearing younger than the stars surrounding them, they upend conventional wisdom about the lifespan of stars. Traditionally, the age of stars within a cluster can be estimated based on their position in the Hertzsprung-Russell diagram. This method assumes that all stars in a cluster formed at roughly the same time and have evolved along predictable paths. Blue stragglers disrupt this narrative, existing as outliers that demand an explanation. The leading theories, binary mass transfer and stellar mergers, are both fascinating in their implications. Binary mass transfer highlights the delicate gravitational interplay between two stars. When one star in a binary system swells into a red giant, it can spill its outer layers onto its companion, rejuvenating it and effectively resetting its evolutionary clock. This process not only creates a blue straggler, but also underscores the transformative power of close gravitational interactions. On the other hand, stellar mergers, where two stars collide and combine into one, represent the more violent side of stellar dynamics, showcasing the chaotic nature of dense star clusters. These theories are not mutually exclusive. In fact, there is growing evidence that both mechanisms might operate simultaneously within the same cluster, depending on the specific conditions. This duality adds to the complexity of studying blue stragglers, as astronomers must disentangle the contributions of each process. Advanced telescopes and spectroscopic techniques are essential for this task, allowing researchers to probe the internal structures and compositions of these stars with unprecedented precision. The role of blue stragglers in the broader ecosystem of star clusters is another area ripe for exploration. Globular clusters, where blue stragglers are most commonly found, are among the oldest structures in the universe, dating back to the early stages of galaxy formation. These clusters are densely packed, with thousands or even millions of stars bound together by gravity. Such crowded conditions create an environment where interactions between stars are inevitable, leading to phenomena like blue stragglers. But the presence of blue stragglers raises deeper questions about the evolution of globular clusters themselves. For example, how do these stars influence the overall dynamics of a cluster? Do their interactions with other stars contribute to the gradual erosion of the cluster's mass, as stars are ejected into interstellar space? And what do blue stragglers reveal about the long-term fate of these ancient structures? By studying these questions, astronomers can gain a better understanding of how globular clusters evolve over billions of years and what role they play in the larger framework of galactic evolution. Interestingly, blue stragglers might also provide clues about the distribution of dark matter within star clusters. Dark matter, the mysterious substance that makes up a significant portion of the universe's mass, does not emit light and cannot be directly observed. However, its presence can be inferred from its gravitational effects. In star clusters, the behavior of stars, particularly outliers like blue stragglers, could offer indirect evidence of dark matter's influence. For instance, the distribution and motion of blue stragglers might reveal subtle gravitational perturbations that could be attributed to dark matter. The implications of blue straggler research extend beyond individual clusters. By comparing the properties of blue stragglers across different environments, such as globular clusters, open clusters, and the galactic field, astronomers can identify patterns and anomalies that shed light on the underlying physics. These comparisons could also reveal how the density and composition of a cluster influence the formation of blue stragglers, providing a window into the conditions that shaped the early universe. Moreover, blue stragglers serve as natural laboratories for studying extreme astrophysical phenomena. Their unusual properties, such as rapid rotation, altered chemical compositions, and high luminosities, make them ideal candidates for testing theories about stellar interiors, fusion processes, and the effects of angular momentum. These stars are not just anomalies. They are key pieces of the cosmic puzzle, offering insights that could reshape our understanding of stellar physics. One of the most exciting frontiers in this field is the search for blue stragglers in other galaxies. While most research has focused on clusters within the Milky Way, advancements in telescope technology have made it possible to identify and study these stars in distant galaxies. Observing blue stragglers in diverse galactic environments could reveal whether the same formation mechanisms are at play or if entirely new processes are involved. Such discoveries would have profound implications for our understanding of star formation and evolution on a cosmic scale. In addition to their scientific significance, blue stragglers hold a certain poetic appeal. They are stars that defy the passage of time, appearing youthful and vibrant in an environment where aging is the norm. Their existence challenges our assumptions about the natural order, reminding us that the universe is full of surprises. They are a testament to the resilience and adaptability of celestial objects, capable of transforming and thriving in ways that seem almost magical. As we continue to study blue stragglers, it is clear that they are more than just a curiosity. They are a gateway to deeper questions about the cosmos. What other phenomena might be waiting to be discovered in the dense cores of star clusters? How do these interactions shape the evolution of galaxies? And what do they reveal about the fundamental forces that govern the universe? The answers to these questions are not just of academic interest. They have the potential to transform our understanding of the cosmos and our place within it. Blue stragglers are a reminder that the universe is a place of infinite complexity, where every answer leads to new questions and every discovery opens the door to further exploration. And so, the study of blue stragglers continues, driven by the same curiosity and wonder that has propelled humanity's exploration of the stars for centuries. With each new observation, each new simulation, and each new insight, we come one step closer to unraveling the mysteries of these enigmatic stars, and in doing so, uncovering the secrets of the universe itself. As we continue to delve deeper into the fascinating world of blue stragglers, it's important to consider the broader implications of these stars on the evolution of galaxies. These stars, often seen as outliers in their clusters, can influence the dynamics of their host galaxies in subtle yet significant ways. Their existence prompts us to question the processes that shape galaxy formation and evolution over cosmic time scales. One intriguing possibility is that blue stragglers could play a role in the formation of new stellar populations within a galaxy. As mentioned earlier, the mechanisms behind blue straggler formation, binary mass transfer and stellar mergers, are events that release vast amounts of energy. These energetic interactions could influence the surrounding star population, creating ripples in the star cluster's density and structure. Such disturbances might, in turn, trigger the formation of new stars in certain areas, leading to the creation of younger, more vibrant stellar populations within an otherwise ancient cluster. This idea dovetails with the larger question of how star clusters evolve over time. Star clusters are not static. They undergo changes that are influenced by a variety of factors, including internal dynamics, external gravitational interactions, and the physical processes that govern star formation and death. Blue stragglers provide a glimpse into this complex evolution, as they are the products of interactions that may alter the cluster's overall age distribution and stellar population. For example, in the densest regions of a globular cluster, where gravitational interactions are most intense, the frequency of stellar mergers and close binary interactions is likely to be higher. This could lead to a higher proportion of blue stragglers in those areas, further complicating the task of determining the true age of a cluster. If these stars are indeed rejuvenated by such interactions, their presence could mask the true evolutionary history of the cluster. This raises the intriguing possibility that clusters with a large number of blue stragglers might, in fact, be older than they appear, with the rejuvenation of certain stars skewing our age estimates. On a larger scale, blue stragglers could also shed light on the interplay between star clusters and the broader galactic environment. While globular clusters are often considered relics from the early universe, isolated from the ongoing processes of star formation and evolution, the discovery of blue stragglers challenges this notion. These stars suggest that even in ancient clusters, new and dynamic processes can still take place, potentially influencing the larger galactic environment. This could have far-reaching implications for our understanding of how galaxies evolve and how star clusters interact with their surrounding interstellar medium. Additionally, the study of blue stragglers in other galaxies, particularly in different types of galaxies, could provide insights into the diversity of stellar environments across the universe. For instance, comparing blue stragglers in elliptical galaxies, which are often dominated by older stellar populations, with those in irregular galaxies, which have ongoing star formation, might reveal differences in the frequency and types of blue straggler formation. This would not only help us understand the processes behind blue stragglers but also contribute to a broader understanding of galactic evolution. On a more speculative note, blue stragglers might even offer a clue as to the existence of life beyond our planet. If these stars are the product of extreme interactions, could similar processes occur in other stellar environments, potentially giving rise to conditions that support life? The energy released by stellar mergers and mass transfer events could have profound effects on the local interstellar medium, perhaps influencing the formation of planets or the chemical evolution of a galaxy. While this is a far-reaching hypothesis, it speaks to the broader potential of blue stragglers to contribute to our understanding of cosmic evolution. As technological advancements in observational tools continue to improve, astronomers are poised to make even more groundbreaking discoveries about blue stragglers. Instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope are already providing unprecedented views of distant star clusters, allowing scientists to study these enigmatic stars in greater detail. With higher resolution images, more precise measurements, and the ability to observe stars across a broader spectrum of wavelengths, the possibilities for new discoveries are endless. One exciting avenue of research is the potential for using blue stragglers as probes of stellar evolution. Because these stars exhibit unusual characteristics, such as high rotational velocities and altered chemical compositions, they could offer valuable insights into the inner workings of stars. For example, studying the surface compositions and spectral lines of blue stragglers could help astronomers understand the mixing processes that occur in stars as they age and evolve. This would deepen our understanding of stellar nucleosynthesis, the process by which stars create the elements that make up the universe around us. Moreover, the discovery of blue stragglers in diverse environments might allow astronomers to test the robustness of stellar evolution models. Are the same physical processes responsible for their formation across all types of star clusters, or do environmental factors play a role in shaping the outcome? By comparing blue stragglers across a range of conditions, astronomers can refine their models of stellar evolution and gain a more nuanced understanding of how stars live and die. In a broader philosophical sense, the study of blue stragglers offers a profound reminder of the mysteries that still await discovery in the universe. While we have made incredible strides in our understanding of the cosmos, the more we learn, the more questions arise. Blue stragglers, with their paradoxical existence and their ability to challenge our assumptions, are a perfect example of the complexity and wonder of the universe. They remind us that the answers we seek may not always be straightforward and that the journey of discovery is as important as the destination. Blue stragglers are far more than just a curiosity in the field of astronomy. They represent a gateway to a deeper understanding of stellar evolution, the dynamics of star clusters, and the larger processes that shape the universe. Their ability to cheat aging challenges our understanding of time itself, forcing us to rethink the way we view the life cycles of stars. As we continue to explore these enigmatic objects, we not only expand our knowledge of the cosmos but also uncover the profound mysteries that lie at the heart of the universe's evolution. The further study of blue stragglers opens the door to a multitude of avenues for exploration, not just within the realm of stellar astrophysics, but in the broader scope of how we understand the universe and our place within it. As we continue to investigate these mysterious stars, we begin to unravel the deeper connections between stellar populations, galaxy evolution, and even the fundamental laws of physics. One of the most significant questions raised by blue stragglers is how they relate to the larger processes of star cluster evolution. Star clusters are natural laboratories for studying the interactions between stars, and the presence of blue stragglers within these clusters provides a unique opportunity to observe how stars evolve in response to internal dynamics. The role of dynamical interactions, such as close encounters, stellar mergers, and binary star evolution, becomes more apparent when we consider these enigmatic stars. As we probe further into the nature of these interactions, we gain insights into the forces that shape the structure and behavior of star clusters over time. In a way, blue stragglers also challenge the classical view of stellar evolution. Traditional stellar evolution theory suggests that stars follow predictable paths based on their mass, age, and chemical composition. However, the existence of blue stragglers, which appear younger and more massive than the majority of the stars in their clusters, suggests that there may be additional factors at play, factors that we have yet to fully understand. This discrepancy prompts the need for a deeper examination of the underlying physics that governs stellar life cycles. One possible explanation for the formation of blue stragglers is the role of binary star systems. In binary systems, two stars orbit each other, and when one star evolves into a red giant, it can transfer mass to its companion. This process, known as mass transfer, can rejuvenate the companion star, increasing its mass and temperature. In some cases, this process may create a blue straggler, an apparently young and hot star that defies the expected age of the cluster. The study of binary star systems, therefore, becomes integral to understanding the formation and evolution of blue stragglers. By examining the frequency and nature of these systems in star clusters, astronomers can gain a better understanding of the mass transfer processes that lead to the creation of these unusual stars. Another important factor in the creation of blue stragglers is stellar collisions. In dense star clusters, stars are packed closely together, and the gravitational interactions between them can lead to close encounters and even collisions. When two stars collide, the result can be a single, more massive star that exhibits characteristics of both progenitors. This process, known as stellar merger, can also produce a blue straggler. The study of star clusters, particularly those with high stellar densities, can shed light on the frequency and mechanisms behind these stellar collisions, and how they contribute to the formation of blue stragglers. The existence of blue stragglers has also sparked interest in the broader field of astrophysical dynamics. These stars represent an intriguing intersection of stellar evolution, binary interactions, and dynamical processes within star clusters. As we continue to develop more sophisticated models of stellar dynamics, we may be able to better understand the conditions under which blue stragglers form, and how they fit into the larger context of star cluster evolution. The role of mass transfer, stellar mergers, and gravitational interactions within dense environments like globular clusters and open clusters can provide new insights into how stellar populations evolve and interact over time. Moreover, the study of blue stragglers can also inform our understanding of the larger-scale dynamics of galaxies. In the context of galactic evolution, star clusters play a crucial role in shaping the structure and chemical composition of galaxies. The presence of blue stragglers in a cluster could, therefore, have implications for the broader evolution of the galaxy. For example, if blue stragglers are more common in certain types of clusters, they could influence the overall stellar population of a galaxy, potentially altering its chemical makeup and star formation history. Additionally, the presence of blue stragglers may also have an impact on the formation of planetary systems. The high mass and temperature of these stars make them prime candidates for the formation of planets, and the process of stellar mergers could even create conditions conducive to the formation of unique planetary environments. By studying blue stragglers, we may uncover new possibilities for the types of planets and ecosystems that could exist around stars with unusual properties. This could, in turn, expand our understanding of the potential for life beyond our own solar system. On a more practical level, the study of blue stragglers has implications for the way we measure the age and distance of star clusters. Because these stars appear to defy the usual age distribution of stars in a cluster, they can introduce uncertainty into our age estimates. If a star cluster contains a significant number of blue stragglers, it may be difficult to accurately determine its true age. This presents a challenge for astronomers who rely on stellar populations to date and map the structure of galaxies. To address this, astronomers may need to develop new techniques for identifying and accounting for blue stragglers in their measurements, ensuring that they don't skew the data. The ongoing study of blue stragglers is also made possible by advances in technology and observational techniques. Telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope provide astronomers with unprecedented views of distant star clusters, allowing for more detailed observations of these stars. In particular, the ability to study blue stragglers in galaxies outside our own, such as those in the local group or even more distant clusters, can offer valuable insights into how these stars behave in different environments. By combining data from multiple observatories and wavelengths of light, astronomers can gain a more comprehensive understanding of blue stragglers and their role in the cosmos. As our observational capabilities continue to improve, we may also be able to observe blue stragglers in real time. This would provide an even more direct view of their formation and evolution, allowing astronomers to witness the processes that give rise to these stars. Observing these events in action would be a major breakthrough in our understanding of stellar dynamics and evolution. In summary, blue stragglers are among the most fascinating and enigmatic objects in the universe. Their existence challenges our understanding of stellar evolution, star clusters, and the dynamics of galaxies. Through the study of these stars, we gain deeper insights into the complex processes that govern the life cycles of stars and the evolution of the universe. While much remains to be discovered about blue stragglers, the progress we have made thus far highlights the incredible potential for future discoveries. As we continue to explore the mysteries of the cosmos, blue stragglers will undoubtedly remain a key focal point in our quest to understand the universe and the forces that shape it. As we delve even deeper into the mystery of blue stragglers, it's important to consider how their study intertwines with the broader cosmic landscape. These stars are not only a puzzle within the context of stellar evolution, but they also offer clues about the early universe and the environments in which stars form. The mechanisms behind their creation could provide answers to some of the universe's most fundamental questions, such as how stellar systems evolve in extreme environments, and how the forces of gravity, mass, and temperature interact at a more granular level. One of the remarkable aspects of blue stragglers is that they appear in various types of star clusters, from open clusters, which are relatively young and loosely bound, to globular clusters, which are older and contain some of the most ancient stars in the universe. The presence of these young, massive stars in ancient clusters suggests that blue stragglers could be integral to understanding the evolution of the cluster itself. The processes that create them, whether through binary star interactions, stellar mergers, or mass transfer, might mirror the dynamic history of these clusters, revealing how star systems evolve over billions of years. Globular clusters, in particular, offer a unique window into the past. These clusters, with their dense concentrations of stars, are thought to be some of the oldest structures in the universe, dating back almost as far as the formation of the first galaxies. Despite their age, the fact that blue stragglers still exist within these clusters raises intriguing questions about their longevity and role in the stellar population. Are they a product of the cluster's past, or do they represent an ongoing process of rejuvenation within the cluster? If they are continually being created, it might suggest that the cluster's dynamics are far from static and that stellar evolution is still an ongoing process, despite the advanced age of the system as a whole. The concept of rejuvenation in the context of blue stragglers also brings attention to the idea that star clusters, particularly the older ones, may not be as dead as once thought. While the stars in these clusters might be older and less active on a large scale, the presence of blue stragglers challenges that notion. Instead, we might reconsider these clusters as being in a state of constant evolution, with new stars being born or renewed in ways that were previously not understood. These stars may, in fact, be a testament to the ever-changing nature of the universe, where even ancient systems can give rise to new life in the form of unexpected stellar phenomena. In addition to their connection to star clusters, blue stragglers also offer a glimpse into the intricacies of stellar dynamics. As mentioned earlier, interactions within dense star clusters, such as close encounters, stellar mergers, and mass transfer in binary systems, are often responsible for the creation of these strange stars. However, one might wonder why these interactions are more common in certain environments than in others. Why do we see a higher concentration of blue stragglers in more crowded clusters, and how does this relate to the fundamental forces at play in such environments? The increased frequency of close stellar encounters in denser environments suggests that the gravitational forces at work in these systems are far more intense than in more isolated regions of space. In a way, the universe becomes a grand laboratory for studying the effects of gravity on stellar evolution. The gravitational interactions within a dense cluster, such as the exchange of momentum during a stellar flyby, can have profound consequences for the stars involved. Some may be flung into eccentric orbits, while others may collide, merge, or transfer mass. These interactions could very well explain the formation of blue stragglers and may be the key to understanding how these stars continue to defy our expectations of stellar aging. It's also important to consider the role that blue stragglers may play in the evolution of the interstellar medium, the vast regions of space between stars filled with gas and dust. When blue stragglers interact with other stars in their cluster, they can cause an influx of material into the surrounding space. Stellar winds, the ejection of mass from these stars, and supernova explosions, all of which may be more common in systems containing blue stragglers, could contribute to the enrichment of the interstellar medium with heavier elements, known as metals. This process of stellar feedback plays a crucial role in the chemical evolution of galaxies and could have important implications for future generations of stars and planetary systems. Understanding how blue stragglers form and evolve can also provide a broader understanding of the potential for life elsewhere in the universe. For instance, the processes that lead to the creation of blue stragglers could also be relevant in the study of planetary systems. If a blue straggler is the product of mass transfer from a companion star, it stands to reason that the star may have a unique chemical composition and evolutionary history that could influence the formation of planets. In fact, it is possible that the presence of blue stragglers in certain regions of space could have an impact on the types of planets that form around them, influencing their size, composition, and even their potential for hosting life. Looking at blue stragglers from a larger perspective, they also raise important questions about the potential for multiple star systems and their impact on planetary formation. Binary and multiple star systems are already known to be important in the study of stellar evolution, but the role of blue stragglers in such systems could offer new insights into the nature of stellar companions, the dynamics of stellar mergers, and the resulting planetary environments. Could the violent processes that create blue stragglers give rise to more habitable conditions for life? This is a tantalizing possibility that could change the way we think about the conditions necessary for life beyond Earth. Additionally, these stars highlight the complexities of cosmic time. While we think of stars as following well-understood life cycles, blue stragglers remind us that not all stars obey these predictable paths. In a way, they are a cosmic anomaly, an exception to the rule. Yet, their very existence encourages us to rethink the rules. Could it be that the entire life cycle of a star, from birth to death, is more flexible than we have ever imagined? Or is there some greater force at work that we have yet to fully comprehend? These questions continue to keep astronomers and physicists on the edge of their seats, pushing the boundaries of what we know and, more importantly, what we are about to discover. With advancements in technology and observational methods, astronomers are poised to explore the phenomenon of blue stragglers with greater depth and clarity. In the future, we may be able to observe these stars not only in our own galaxy but across vast distances, unveiling their role in distant clusters and galaxies. As we peer further into the cosmos, we may uncover new classes of blue stragglers and new mechanisms behind their formation. Perhaps we will even develop new theories of stellar evolution that account for the complexities and unpredictability of these enigmatic stars. The study of blue stragglers is, without a doubt, one of the many stepping stones to a deeper understanding of the universe. A universe that is full of surprises, ready to reveal its secrets when we are ready to listen. As we continue to explore the mystery of blue stragglers, it's essential to consider the broader implications of these stars not only on our understanding of stellar evolution but also on our understanding of the universe itself. Blue stragglers challenge conventional thinking, forcing us to reconsider our models of how stars live and die. These stars, in their strange defiance of aging, may hold the key to unlocking some of the universe's most profound secrets. One of the most intriguing aspects of studying blue stragglers is how they bring into focus the interplay between stellar dynamics and the environments in which they exist. In some ways, they serve as a bridge between the isolated, individual life cycles of stars and the complex, interconnected systems of star clusters. It's easy to think of stars as solitary objects, following a predictable path from birth to death. But blue stragglers complicate this narrative, showing us that stellar evolution is not always as linear or predictable as we might like to believe. These stars don't just follow the expected path. They create their own story, shaped by their interactions with other stars, the gravitational forces of their environment, and the mass they acquire or lose over time. What's fascinating is how blue stragglers highlight the fact that stars are not entirely at the mercy of time and space. While we often think of stars as being subject to an inevitable progression through their life cycle, from the birth of a star in a nebula to its eventual death in a supernova or other end-of-life event, blue stragglers show us that these processes are not set in stone. In certain environments, stars can cheat the passage of time, appearing younger and more massive than their neighboring stars. This phenomenon challenges our understanding of how stars evolve and how they interact with their surroundings. It's important to note that blue stragglers are not just an anomaly. They are a window into the complex and often unpredictable nature of the cosmos. Their existence forces us to confront the reality that, even in a universe governed by natural laws, there is room for exceptions, anomalies, and unexpected phenomena. Blue stragglers are a testament to the dynamic, ever-changing nature of the universe, a place where even the most well-established theories can be upended by the discovery of something entirely new. In this sense, they are more than just an interesting curiosity. They are a challenge to the way we think about the universe and our place within it. The study of blue stragglers also provides an opportunity to re-examine the evolution of star clusters, which are some of the oldest and most enduring structures in the universe. These clusters contain populations of stars that have been gravitationally bound together for billions of years, and their study provides valuable insights into the early history of the cosmos. But the presence of blue stragglers within these ancient clusters complicates the picture. If these stars are still being created today, it suggests that star clusters are not static, unchanging systems. Instead, they may be in a state of ongoing evolution, with new stars being born or rejuvenated through processes we don't fully understand. This realization could have far-reaching implications for our understanding of the broader structure of the universe. If star clusters are still capable of generating new stars, could this process extend beyond the clusters themselves? Could entire galaxies still be giving birth to new stars in ways that we haven't yet detected? The discovery of blue stragglers in ancient clusters opens up the possibility that the universe is not as dead as we once thought. Even in the oldest and most stable environments, new life can emerge in the form of stars and potentially even planets. This has profound implications for our understanding of galactic evolution and the potential for life elsewhere in the universe. In addition to their role in star cluster dynamics, blue stragglers also raise intriguing questions about the nature of stellar populations more broadly. In many cases, these stars are found in the company of older, less active stars, creating a stark contrast between the two. But why do some star systems contain blue stragglers while others don't? What is it about the environment, or the interactions between stars that leads to the creation of these young, energetic stars in the midst of an aging population? The answers to these questions may help to clarify the factors that drive stellar evolution and the formation of different types of stellar populations. Another important aspect of studying blue stragglers is the potential for using them as cosmic laboratories. Because these stars are created through interactions with other stars, they offer a unique opportunity to study the forces that shape the evolution of stars and their environments. By studying blue stragglers, astronomers can learn more about the physics of stellar mergers, the effects of mass transfer, and the processes that lead to the rejuvenation of stars. These insights could help to refine our models of stellar evolution, shedding light on the mysteries of how stars form, live, and die. Furthermore, the study of blue stragglers can also deepen our understanding of binary and multiple star systems. In many cases, blue stragglers are created through the interaction between two stars in a close binary system. These interactions can result in the transfer of mass between the two stars, leading to the formation of a more massive and younger-looking star. This process, known as mass transfer, can have profound effects on the evolution of both stars in the system. By studying blue stragglers, astronomers can gain new insights into the dynamics of binary and multiple star systems, and how these systems evolve over time. The implications of blue straggler research extend beyond just the field of stellar evolution. These stars could also play a role in our understanding of galaxy formation and evolution. Star clusters, particularly those containing blue stragglers, are often seen as building blocks of larger galactic structures. By studying the properties of these clusters and their constituent stars, astronomers can learn more about the processes that lead to the formation of galaxies and the evolution of their stellar populations. If blue stragglers are indeed created through interactions within star clusters, their presence could provide valuable clues about the early history of galaxies and the processes that shaped their development. Additionally, the study of blue stragglers may offer new perspectives on the search for extraterrestrial life. The unique environments in which these stars exist, dense, highly interactive regions of space, could be conducive to the formation of planets and other celestial bodies. If blue stragglers are indeed part of a larger, ongoing process of star formation and rejuvenation, it's possible that planets in these systems could also be undergoing similar processes of renewal. This could have significant implications for our understanding of the potential for habitable worlds beyond Earth and the conditions necessary for life to arise. Blue stragglers are far more than just a curious anomaly in the study of stellar evolution. They are a key piece of the puzzle in understanding the complexities of the universe, from the evolution of star clusters to the formation of galaxies and even the potential for life beyond our planet. These strange stars challenge our expectations, forcing us to rethink what we know about the cosmos and the forces that shape it. As our observational techniques and theoretical models continue to advance, it's likely that blue stragglers will remain at the forefront of our exploration of the universe, offering new insights and challenges for astronomers and physicists alike. Their study is far from over, and as we learn more about these enigmatic stars, we may uncover even more mysteries that will continue to shape our understanding of the universe and our place within it. The fascinating tale of blue stragglers is just beginning, and who knows what secrets these stars will reveal as we continue to explore the cosmos. As we continue to explore the complexities of blue stragglers, we should dive deeper into the various theories and models that attempt to explain how they come into existence. At the heart of these theories is the idea that the formation of blue stragglers is not a simple, isolated phenomenon but rather a complex process that involves interactions between stars, mass transfer, and the dynamics of the environments they inhabit. One of the most widely accepted explanations for the creation of blue stragglers revolves around the concept of stellar mergers. Stellar mergers occur when two stars in a binary or multiple star system collide and combine into a single, more massive star. This process results in the creation of a star that appears younger and more massive than its counterparts in the same star cluster. In this case, the merging stars may have been on different evolutionary paths, with one star being older and the other younger. When they merge, the resulting star takes on characteristics of both, appearing younger and more luminous than the surrounding stars, which are typically much older. This explanation fits well with the observed characteristics of blue stragglers. These stars are often found in dense star clusters, particularly globular clusters, where stars are packed closely together, making stellar interactions more common. In such environments, gravitational interactions are frequent, and the chances of stars coming into close contact, or even merging, are higher. As a result, the presence of blue stragglers in these clusters can be understood as the outcome of these frequent interactions. However, not all blue stragglers are the result of stellar mergers. Some researchers suggest that these stars can also form through the process of mass transfer in a binary star system. In this scenario, one star in the binary system is much larger than the other and begins to transfer material onto its companion star. This transfer of mass can cause the smaller star to increase in mass and luminosity, rejuvenating it in the process. The result is a star that appears younger than its neighbors, even though it has been part of the same stellar population for a much longer time. This process of mass transfer is complex and can take many forms, depending on the size, composition, and orbital dynamics of the stars involved. For instance, in some cases, the mass transfer can be unstable, causing the smaller star to experience rapid changes in its structure. In other cases, the mass transfer may be more stable, allowing the star to gradually accrete material and increase its mass over time. Regardless of the specific process, the outcome is the same. The smaller star is rejuvenated and becomes a blue straggler, appearing younger and more massive than its peers. Another intriguing possibility for the formation of blue stragglers involves the interaction between stars and the environment of the star cluster itself. Star clusters are not static systems. They are dynamic environments where stars are constantly moving and interacting with one another. Over time, these interactions can lead to the creation of new stars or the rejuvenation of old ones. In the case of blue stragglers, this means that the stars may be receiving additional mass from their surroundings, either through direct accretion from nearby stars or through the gravitational influence of other objects in the cluster. For example, in some clusters, the gravitational forces of nearby stars or even black holes could cause stars to exchange material, leading to the formation of new, more massive stars. These interactions could also cause older stars to become rejuvenated, effectively cheating the aging process and creating the appearance of blue stragglers. The dense, crowded environments of star clusters create the perfect conditions for these types of interactions, and they may be a key factor in the formation of blue stragglers. There is also the possibility that blue stragglers may be the result of a more exotic process, such as the interaction between stars and the remnants of dead stars, like white dwarfs or neutron stars. In these cases, the mass transfer from a compact object to a regular star could result in a sudden increase in the mass and luminosity of the star, turning it into a blue straggler. These types of interactions are more rare but still plausible, especially in regions of space with high stellar density and a significant number of compact objects. Despite the variety of possible explanations for the formation of blue stragglers, one thing is clear: they represent a fascinating and important puzzle in the study of stellar evolution. By understanding how these stars are created, we gain valuable insights into the broader processes that govern the life cycles of stars and the dynamics of star clusters. Additionally, the study of blue stragglers helps us to refine our models of stellar evolution and to better understand the complex interactions between stars and their environments. Beyond the technical explanations, the discovery and study of blue stragglers have broader implications for our understanding of the universe itself. These stars are a reminder that the cosmos is full of surprises, and that even the most well-established theories can be upended by the discovery of an anomaly. Blue stragglers challenge our assumptions about the uniformity of stellar populations and force us to rethink what we know about how stars evolve, interact, and die. In many ways, blue stragglers are a symbol of the mysteries that still await us in the universe. They represent the unexplored frontiers of stellar science, a reminder that there is still much we don't know about the processes that shape the stars and galaxies around us. As our observational tools and techniques continue to improve, it's likely that we will discover even more about these strange and enigmatic stars, revealing new layers of complexity in the universe's vast and intricate web. What's more, the study of blue stragglers could help us answer some of the most profound questions about the universe, including the nature of dark matter and dark energy. These mysterious components of the universe make up the vast majority of its mass and energy, yet we know very little about them. By studying the dynamics of star clusters and the forces that lead to the formation of blue stragglers, we may be able to uncover new clues about the nature of dark matter and how it interacts with ordinary matter. In this sense, blue stragglers could be the key to unlocking some of the most fundamental mysteries of the cosmos. Looking ahead, the future of blue straggler research is bright. With new telescopes and observatories being built, we will have the ability to study these stars in greater detail than ever before. Advances in computational modeling and simulations will allow us to create more accurate models of stellar evolution, taking into account the complex interactions that lead to the formation of blue stragglers. And as our understanding of the universe continues to evolve, we may find that blue stragglers are not just a curiosity, but a central piece of the puzzle that helps us understand the nature of stars, galaxies, and the cosmos itself. Blue stragglers are among the most fascinating and enigmatic objects in the universe. Their defiance of the natural aging process challenges our understanding of stellar evolution and the dynamics of star clusters. Through the study of blue stragglers, we can gain new insights into the complex and dynamic nature of the universe, while also refining our models of how stars form, live, and die. As we continue to explore the cosmos, these strange and beautiful stars will no doubt remain at the forefront of our quest to understand the fundamental processes that govern the universe. As we delve deeper into the study of blue stragglers, we start to realize just how much they can teach us about the wider universe. These stars are not just anomalies. They are windows into some of the most profound cosmic processes. By understanding how they form, evolve, and behave, we can begin to piece together larger questions about the forces at play in star clusters and the broader structures of galaxies. One of the biggest questions that blue stragglers present is how the age of a star can be misleading. In most cases, scientists rely on the principle that stars of similar mass, chemical composition, and environment should evolve in similar ways. Typically, older stars are less luminous and cooler, and their color shifts to red as they run out of fuel. But blue stragglers break this rule. These stars are blue and bright, even though they are found in clusters that should be filled with older, redder stars. Their youthful appearance suggests that they have somehow reset their aging process, and this paradox challenges our conventional models of stellar evolution. The mystery of blue stragglers brings us back to the heart of what it means to study stellar populations. Every star cluster, from the smallest open clusters to the largest globular clusters, is a cosmic experiment, a group of stars born from the same molecular cloud, formed at roughly the same time, and existing in the same environment. Ideally, stars within a cluster should have similar characteristics, such as size, mass, and age. The older the cluster, the older the stars within it should be. However, blue stragglers violate this expectation by appearing much younger than they truly are, casting doubt on the assumption that stellar age can be reliably determined simply by observing a star's color and brightness. This opens up a deeper question about how we define the age of a star. Traditionally, stellar age has been calculated using models that predict how a star will evolve over time. By measuring the mass and brightness of a star, astronomers can estimate how much time has passed since the star began its life on the main sequence. However, blue stragglers challenge this model by appearing to have restarted their life cycle, leaving scientists to question whether there might be other mechanisms at play that we have yet to understand. Understanding blue stragglers might also provide insight into the larger context of galactic evolution. Star clusters are thought to be the building blocks of galaxies, and the processes that occur within them help shape the evolution of the galaxy as a whole. By studying the life cycles of stars within clusters, we can learn more about the forces that drive the formation and destruction of galaxies. The presence of blue stragglers might indicate that star formation within a cluster is not as simple as we once thought. These stars may form from interactions that are not fully understood, suggesting that the process of stellar birth and death is far more complex than our current models can account for. Furthermore, the study of blue stragglers offers an opportunity to explore the conditions that allow stars to survive longer than expected. This could be particularly important in understanding the behavior of stars in extreme environments, such as those near black holes or in the dense cores of star clusters. In these regions, stars may experience strange interactions and forces that lead them to evolve in ways that we don't typically observe in other areas of the universe. In a sense, blue stragglers act as beacons that help us understand how stars behave under extreme conditions, offering clues about the physical processes that govern stellar life. Interestingly, blue stragglers may also hold clues about the future of our own Sunday. While the Sun will not become a blue straggler, the way stars like our Sun evolve over time could help us better understand the mechanisms that sustain stellar life. The Sun is expected to eventually expand into a red giant, and then shed its outer layers to become a white dwarf. However, the processes that occur as it ages are still not fully understood, and the study of blue stragglers may provide new insights into the later stages of stellar evolution. It is also worth mentioning that the study of blue stragglers is closely tied to the evolution of the universe itself. By examining the stellar populations in different types of clusters, astronomers can learn about the conditions that existed in the early universe. The process by which stars form, live, and die can reveal a great deal about the environment in which galaxies and stars were born. In the case of blue stragglers, understanding their formation could provide clues about the dynamics of the early universe, when conditions were vastly different from what we observe today. While we've explored various theories that attempt to explain the origin of blue stragglers, it's important to acknowledge that the true mechanism behind their formation remains elusive. Each explanation brings new insights, but none of them can fully account for the diversity of blue straggler stars that we observe. This suggests that there may be more than one way for these stars to come into existence, and we must continue to develop new models to better understand their origins. One particularly intriguing area of research is the role of blue stragglers in the evolution of binary and multiple star systems. As we know, star clusters often contain a large number of binary stars, pairs of stars that orbit each other. In such systems, the gravitational interaction between the two stars can lead to complex dynamics, including the possibility of stellar mergers or mass transfer events. These interactions can give rise to blue stragglers, which appear to defy the normal rules of stellar aging. By studying these systems in greater detail, astronomers can gain a better understanding of the conditions that lead to the formation of blue stragglers, as well as how these stars influence the overall evolution of the cluster. The study of blue stragglers is far from over. These stars remain one of the most fascinating puzzles in modern astrophysics, challenging our understanding of stellar evolution, star cluster dynamics, and the broader processes that shape the universe. With each new observation and discovery, we edge closer to unraveling the mysteries behind these enigmatic stars, shedding light on the forces that govern the life cycle of stars. As we continue to explore the universe, the study of blue stragglers will no doubt remain an essential part of our quest to understand the cosmos in all its complexity. And who knows? Perhaps the answers to some of the universe's most profound questions lie hidden in these mysterious, youthful stars that seem to defy the passage of time. As we continue to unravel the mysteries of blue stragglers, it becomes clear that these stars represent more than just outliers in stellar evolution. They symbolize the intricate complexity of the universe and the constant need to challenge our understanding of how stars live, interact, and evolve. The discovery of these stars forces us to rethink fundamental aspects of astrophysics and astronomy, especially regarding how we classify and predict the behavior of stars within clusters. To fully appreciate the significance of blue stragglers, it's essential to understand their place within the context of stellar evolution. Traditionally, astronomers have followed the model of stellar evolution that was proposed in the early 20th century, which states that stars are born from molecular clouds, spend the majority of their lives fusing hydrogen into helium in their cores, and eventually expand into red giants before shedding their outer layers to become white dwarfs. This process is predictable, and the progression of a star's life can be traced with great accuracy based on its mass, temperature, and chemical composition. However, the existence of blue stragglers challenges this predictability by introducing a kind of wild card into the equation. One of the most fascinating aspects of blue stragglers is that they appear to have bypassed the normal stages of stellar aging. Instead of evolving into red giants or supernovae as older stars do, blue stragglers maintain the characteristics of younger, more massive stars. This suggests that they may not have followed the typical evolutionary path that other stars in the same cluster have followed. The question, then, is why do they appear to be so young? The answer to this question lies in the possibility that blue stragglers are the result of stellar interactions within their cluster environments, specifically through processes such as mergers or mass transfer. The process of stellar mergers, where two stars collide and combine into a single, more massive star, could explain the youthful appearance of blue stragglers. This phenomenon is particularly common in dense star clusters, where stars are packed together closely enough to experience gravitational interactions. These interactions can cause two stars to spiral inward toward each other, eventually colliding and merging into one larger star. The result is a star that is far more massive than its original components, and it is this increased mass that allows it to burn more brightly and maintain a blue hue. Another potential explanation for blue stragglers is the process of mass transfer in binary star systems. In a binary system, one star may be more massive than the other, causing it to evolve faster. In such cases, the more massive star can shed material onto its smaller companion, transferring mass and rejuvenating the smaller star. This mass transfer process can cause the companion star to gain additional fuel, allowing it to continue burning at a rate that would be typical for a younger star. The result is a blue straggler that appears to be much younger than the rest of the stars in its cluster, despite being part of an older population. These interactions in binary systems are not limited to just one or two stars. The interactions within a star cluster are incredibly complex, and the presence of multiple stars in close proximity increases the likelihood of unusual stellar events. In some cases, blue stragglers could form from a combination of stellar mergers, mass transfer, and other forms of gravitational interactions, all of which can lead to the formation of stars that defy conventional expectations of age and behavior. The discovery of blue stragglers in star clusters has also led astronomers to rethink the evolution of star clusters themselves. Star clusters are thought to be the oldest building blocks of galaxies, and they contain stars that formed at roughly the same time from the same molecular cloud. As such, they provide a snapshot of stellar evolution at different stages of life. However, the presence of blue stragglers complicates this picture, suggesting that stellar interactions within the clusters can have a profound impact on the cluster's overall development. The processes that lead to the formation of blue stragglers may be influencing the cluster's overall age distribution, meaning that the simple assumption of a uniform stellar population may not always be valid. This realization has profound implications for the study of galaxy evolution. Star clusters are thought to play an important role in the formation and growth of galaxies, and the processes that occur within them could influence the way galaxies evolve over time. Blue stragglers, as products of complex stellar interactions, may offer important insights into the dynamics of these clusters and their role in the formation of larger galactic structures. By studying these stars in greater detail, we can learn more about the factors that drive galaxy formation and evolution. In addition to their role in galaxy evolution, blue stragglers may also offer clues about the future of our own solar system. As we look toward the future of the Sun, we know that it will eventually exhaust its supply of hydrogen and begin to evolve into a red giant. This process will lead to the expansion of the Sun's outer layers, and it will eventually shed its outer envelope, leaving behind a white dwarf. However, the exact mechanisms that govern the later stages of stellar evolution are still not fully understood, and the study of blue stragglers could provide important insights into these processes. By understanding how stars like the Sun evolve in extreme environments, we can gain a better understanding of the forces that will shape our own solar system in the distant future. Moreover, studying blue stragglers allows us to explore the physical processes that take place during stellar mergers and mass transfer. These phenomena are not limited to star clusters. They also occur in other regions of the universe, such as the centers of galaxies or in the vicinity of black holes. By studying the formation of blue stragglers, astronomers can gain valuable insights into the behavior of stars in these extreme environments, helping to shed light on some of the most mysterious and dynamic regions of the universe. As we look ahead, it's clear that the study of blue stragglers will continue to be a key area of research in astrophysics. These stars present a unique opportunity to explore the complex interactions that govern the evolution of stars and star clusters. While we have made significant progress in understanding the formation and behavior of blue stragglers, much remains to be discovered. New observations, advances in computational modeling, and the development of new technologies will undoubtedly reveal even more about these fascinating stars and the processes that shape their evolution. Blue stragglers remind us that the universe is full of surprises, and the more we learn, the more we realize how much we have yet to understand. These stars, which seem to defy the normal rules of stellar evolution, challenge us to rethink our assumptions about the cosmos. As we continue to explore the stars and the mysteries they hold, we may find that the true story of the universe is far more complex and unexpected than we could have ever imagined. As we continue our exploration of blue stragglers, we are left to wonder, how do these peculiar stars fit into the broader cosmic picture? To answer this, we must consider the environments in which these stars are found, the conditions that contribute to their formation, and the larger implications of their existence for our understanding of stellar evolution. The complexity of blue stragglers challenges not only the theories of stellar formation but also how we perceive the processes that govern the life cycles of stars, clusters, and galaxies themselves. One crucial factor that influences the formation of blue stragglers is the density of their environment. These stars are most commonly found in dense stellar clusters, where stars are packed in close proximity to each other. In such environments, the gravitational forces acting on the stars are much stronger than in more sparse regions of space. The denser a star cluster is, the more likely it is that stars will interact with each other. These interactions can take the form of close encounters, gravitational capture, or even outright collisions, all of which can lead to the formation of blue stragglers. The dense conditions in star clusters increase the likelihood of such stellar mergers and interactions, which in turn contributes to the creation of stars that appear much younger and more massive than their neighbors. This is a clear deviation from the typical expectations for a star cluster, where the stars are supposed to evolve in a uniform manner, all at roughly the same rate. The discovery of blue stragglers in these environments suggests that the interactions between stars in such dense clusters can be significant enough to alter the normal course of stellar evolution. But the formation of blue stragglers is not restricted to star clusters alone. While these stars are most commonly found in these dense regions, they have also been observed in other areas of the universe, including in the outskirts of galaxies and in the cores of globular clusters. This suggests that the mechanisms that produce blue stragglers are not limited to a single type of environment. In fact, some researchers have proposed that these stars might be more widespread than we previously thought, potentially existing in a variety of different cosmic settings. The broad distribution of blue stragglers raises the question of whether their formation is tied to specific stages in the evolution of a star cluster or if they represent a more universal process that occurs throughout the universe. The fact that they appear in a range of different environments suggests that they may be a common feature of stellar systems, and that the forces driving their formation are an inherent part of the cosmic landscape. The more we learn about these stars, the more we realize that they could provide valuable insights into the larger processes of star formation, galaxy evolution, and cosmic dynamics. In addition to their implications for stellar evolution, blue stragglers have also opened up new avenues for research into the interaction between stars and their environment. As we mentioned earlier, blue stragglers are often the result of stellar mergers or mass transfer in binary systems. These interactions offer a rare opportunity to study the intricate processes that govern the behavior of stars in close proximity to one another. Through the study of blue stragglers, astronomers can gain a deeper understanding of how stars interact, how mass is transferred between them, and how the dynamics of star clusters influence the overall behavior of the system. In recent years, advancements in technology and observational techniques have allowed astronomers to study blue stragglers with greater precision. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have provided invaluable data on the characteristics of these stars, allowing scientists to gain new insights into their formation and evolution. Additionally, the use of computer simulations and modeling techniques has enabled astronomers to recreate the conditions under which blue stragglers form, providing a better understanding of the physical processes that drive their creation. These new tools have also allowed for the discovery of blue stragglers in previously unexplored regions of space. For example, astronomers have recently identified blue stragglers in more distant star clusters, expanding our knowledge of their distribution across the universe. These discoveries are helping to shed light on the role that blue stragglers play in the larger cosmic picture, and they are pushing us closer to answering the fundamental question: why do these stars exist? And what do they tell us about the universe? One of the key aspects of blue stragglers that has intrigued scientists is their potential to shed light on the physics of stellar mergers and mass transfer. While the formation of these stars is relatively well understood, the precise mechanisms that govern these processes are still a topic of ongoing research. By studying the behavior of blue stragglers, astronomers can gain insights into how stars interact in dense environments, how energy and mass are transferred between them, and how these interactions can alter the overall evolution of a star cluster. As we continue to study blue stragglers and their role in the cosmos, it's important to recognize that these stars represent a deeper mystery: the true nature of stellar evolution itself. For many years, scientists have believed that stellar evolution follows a predictable path, with stars evolving from main sequence stars to red giants, and eventually to white dwarfs. However, the existence of blue stragglers suggests that this process is not as straightforward as we once thought. These stars defy the conventional wisdom of stellar evolution, and in doing so, they challenge us to reconsider our understanding of the life cycles of stars. This is where blue stragglers become so fascinating. They serve as a reminder that the universe is far more complex than we can fully comprehend. Every new discovery in astronomy forces us to revise our theories, to expand our models, and to rethink what we know about the cosmos. The study of blue stragglers is just one example of how the universe continually surprises us, showing us that there is always more to learn, more to explore, and more to discover. Ultimately, the mysteries of blue stragglers illustrate a key point about the nature of scientific inquiry. Our understanding of the universe is always evolving. As new technologies emerge, and as we push the boundaries of what we can observe and measure, we are continually reshaping our models of the universe. The existence of blue stragglers, with their defiance of standard stellar evolution theories, is a perfect example of how science is a never-ending process of discovery, refinement, and rethinking. In the years to come, we will undoubtedly learn more about these enigmatic stars and the processes that shape their formation. Whether through advances in observational technology, new theoretical models, or unexpected discoveries, the study of blue stragglers promises to offer even more insights into the universe's most fundamental questions. As we continue to explore the mysteries of the cosmos, we will undoubtedly find that the answers to our questions often lead to even more profound and perplexing mysteries, reminding us just how much we still have to learn. As our journey into the fascinating world of blue stragglers continues, we begin to ask ourselves, what role do these stars play in the larger evolution of star clusters, galaxies, and even the universe itself? Understanding the significance of blue stragglers goes beyond just investigating their peculiar existence. Their presence in star clusters, and the mysterious mechanisms that bring them into being, could hold the key to unlocking deeper secrets about the fundamental processes that drive the universe. One area where blue stragglers could provide valuable insights is in the study of stellar populations. In astronomy, a stellar population refers to a group of stars within a galaxy or star cluster that share similar characteristics, such as age, metallicity, and evolutionary stage. Traditionally, these populations have been used to trace the history of star formation and the evolution of galaxies. However, the presence of blue stragglers complicates this picture, as these stars seem to defy the age constraints typically associated with their host populations. In a star cluster, for example, most stars are expected to have formed around the same time and will therefore be of roughly the same age. This creates a kind of cosmic fingerprint that allows astronomers to measure the age of the cluster. However, the existence of blue stragglers, which appear to be much younger than the rest of the cluster, raises questions about this method of dating stellar populations. These stars effectively cheat the expected aging process, challenging astronomers to reconsider the ways in which we measure the age of star clusters and, by extension, the age of galaxies themselves. This challenge also extends to our understanding of how stellar populations evolve over time. If blue stragglers are indeed the product of stellar mergers or mass transfer events, they represent a distinct phase in the evolution of a star cluster. These events may occur at different rates in different clusters, depending on factors such as cluster density, stellar interactions, and the overall gravitational dynamics of the system. As such, blue stragglers could serve as markers of specific stages in the evolution of a star cluster, providing astronomers with a unique tool for studying the complex processes that govern stellar evolution. But what about their larger cosmological significance? Could blue stragglers offer clues about the way galaxies form and evolve? As we mentioned earlier, these stars are often found in dense stellar environments, such as globular clusters, which are among the oldest structures in the universe. By studying the formation and evolution of blue stragglers in these ancient clusters, astronomers can gain a better understanding of the processes that shaped the early universe. These stars could serve as relics of the first generations of stars, offering a glimpse into the conditions that prevailed during the earliest phases of galaxy formation. In this context, blue stragglers could also be linked to the broader concept of galaxy evolution. The presence of these stars in both young and old stellar populations suggests that their formation is not limited to a single epoch in the history of the universe. Instead, they could be indicative of a more general process that operates throughout the life of a galaxy. In this way, blue stragglers could be seen as both a product and a reflection of the dynamic forces that shape galaxies over cosmic time. Moreover, the study of blue stragglers could have implications for our understanding of dark matter. While this may seem like an unlikely connection, the processes that create blue stragglers, stellar mergers, mass transfer events, and gravitational interactions, could provide valuable insights into the distribution of dark matter within galaxies. Since dark matter exerts a strong gravitational influence on the motion of stars, it could play a significant role in shaping the environments where blue stragglers form. Understanding the relationship between blue stragglers and dark matter could, in turn, help refine our models of galaxy formation and the distribution of matter throughout the cosmos. The role of blue stragglers in star clusters also brings us to the topic of stellar dynamics, the study of how stars move and interact within a gravitationally bound system. The dense environments of star clusters are prime laboratories for studying these dynamics, and blue stragglers play a crucial role in the process. As we've already seen, these stars can form through a variety of mechanisms, including stellar mergers and mass transfer events. These interactions often occur as a result of the gravitational forces acting within the cluster, which can cause stars to move closer together and interact more frequently. In some cases, the interaction between stars in a cluster can lead to the formation of binary or even triple star systems. These systems can be especially important for the creation of blue stragglers, as mass transfer between stars in a binary system is one of the primary ways in which these stars are formed. The gravitational dynamics of a star cluster, therefore, play a central role in determining whether or not blue stragglers will emerge. Interestingly, the presence of blue stragglers in star clusters can also provide clues about the overall stability of these systems. If a cluster contains a significant number of blue stragglers, it may indicate that the cluster is undergoing a period of intense dynamical activity. This could be the result of the cluster experiencing high rates of stellar interactions, which could lead to the formation of more blue stragglers. Conversely, a lack of blue stragglers in a cluster might suggest that the cluster is relatively stable, with fewer stellar interactions taking place. These insights into the dynamics of star clusters could have broader implications for our understanding of how galaxies evolve. Since star clusters are often considered to be the building blocks of galaxies, the processes that occur within them can provide important clues about the formation and evolution of galaxies as a whole. By studying the dynamics of star clusters and the role of blue stragglers within them, we can gain a deeper understanding of the forces that shape galaxies over time. The study of blue stragglers also raises important questions about the future of star clusters themselves. While these stars are often thought to be the result of interactions within the cluster, their long-term fate is still a subject of much debate. Will blue stragglers eventually burn out and become white dwarfs or black holes? Or will they continue to exist as anomalous stars, defying the normal patterns of stellar evolution? Some astronomers believe that blue stragglers may eventually be ejected from their parent star clusters. This could happen if the gravitational interactions within the cluster become so intense that the blue stragglers are flung out into intergalactic space. Alternatively, blue stragglers could continue to evolve within their clusters, eventually reaching the end of their life cycles and transitioning into white dwarfs or other types of remnants. The future of blue stragglers may also depend on the fate of the star clusters themselves. Over time, star clusters can lose their stars through a process called evaporation, in which the stars are gradually scattered into the surrounding space. If this happens, blue stragglers may be left without a stable environment in which to exist, leading to their eventual dissolution. However, if star clusters remain intact for longer periods of time, blue stragglers could continue to survive and evolve within their gravitationally bound systems. In either case, the long-term existence of blue stragglers adds another layer of intrigue to their already fascinating story. These stars, which are born from unusual stellar interactions and deviate from the standard model of stellar evolution, may continue to exist and evolve in unexpected ways, challenging our understanding of the universe for years to come. In the end, blue stragglers serve as a reminder that the universe is full of mysteries, and that our understanding of the cosmos is constantly evolving. These stars, which defy conventional expectations and challenge our theories of stellar evolution, remind us that there is always more to discover and learn. As we continue to study these enigmatic objects, we may uncover new insights into the fundamental processes that shape the universe, and perhaps even find answers to some of the most profound questions in science. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.